Hello, my name is Matthew Nealon, and this is video 1 for Homework Assignment 5. In this video, we're going to be figuring out the stoichiometry for our adiabatic flame with the given products that are entering the system as the flame is being produced. So let's begin. So the first thing we have is our flame, or the Bunsen, or let's just say it's a Bunsen burner that's creating our flame. So we will just set it as such. And just to give a little visual representation, we have just a flame being produced here. So this is our flame. And what we can say about this is that our intakes, we have two of them. To produce a flame, we need a natural gas and we need air. And you might be thinking, what goes into our natural gas and our air that's being reacted here? So to form our combustion reaction to form our flame. So we'll then separate off what is going to be used in our reaction here. So we'll start with our natural gas side, and then we will also have an air side. So natural gas. So what goes in with our natural gas? Well, there's three components that we're specifically using for our natural gas. Our natural gas is going to be composed of three separate compounds that have different percentages in which they're being represented, which is methane, ethane, and propane. And the ratios, or more the percentages of each compound that's being used, is that our methane is going to be our majority, which is going to be 95%. 95% of all the natural gases being reacted is going to be methane. We have 4% ethane, and then we have 1% propane. And the reason why we need to know these percentages is because each one of our natural gases that's going to be reacting with our air has a different temperature that's going to be achieved with each compound that's being used. So we need to calculate, or we need to find out the ratios in which our products are being used, or our reactants to our products. And we need to figure out how that's going to relate to each other in the long term, to figure out how the temperature is going to be produced. And in our air, since we're using normal atmospheric air, is that we have a ratio between two molecules. We have our oxygen and we have our nitrogen. And since this is made, and there are a ratio between these two as well, this ratio is going to be 21 to 79, or every time there's 21 molecules of oxygen, there's going to be 79 molecules of oxygen, just to form a 100% ratio between them. And with this, we can then start finding out what our stoichiometry is going to be. So first, let's come down here. We will then define our normal combustion reaction. A normal combustion reaction is then going to be represented with this chemical equation. It's going to be our methane molecule reacting with two molecules of our oxygen, and then it's going to react into CO2, carbon dioxide, plus two molecules of our water, H2O. This is our normal combustion reaction. However, if you've noticed, we're using normal air. This only represents the portion of our oxygen reaction, or the oxygen that's being put into it. However, we're not using normal oxygen or pure oxygen. We are using normal air, which is comprised of oxygen and nitrogen. So we need to include that in our equations, and we will separate that off as such or include that. So we will just go down the list and see what our ratios are going to be. Since we already have our methane reaction, we're just going to rewrite this equation in terms with our nitrogen being included in both sides of the of our chemical reaction. So we'll just separate this off, our methane, and then our methane reaction, it's just going to be the same equation up there. So it's going to be 1 carbon, 4 hydrogen, plus 2 oxygen. And then, since we have two molecules of oxygen being produced, we also know that 2 of our nitrogen is going to be produced, but we need to include this ratio up here. So we need to include 79 over 21, our ratio compared to oxygen nitrogen included in this. So this is our left side of the equation, our reactants that we're putting in. And then we then have CO2 plus 2 molecules of water plus our nitrogen. And we know with this that our nitrogen is not going to react with our system. So it's going to be so this is our methane reaction. And as you can tell already, is that our nitrogen did not react, or it's not being included in our reaction because our carbon isn't going to react with our nitrogen in our combustion reaction. But we do need to include it in our chemical equations because it will have an effect on the temperature that's going to get produced from this flame up here. So we need to include our nitrogen. So our next thing that we're going to do is our ethane reaction. Underline that. And this will be our ethane reaction. And ethane is slightly different than our methane. It has more carbon and more hydrogen compared to what we have. So our ethane is going to be 2 carbons and then 6 hydrogens. And if you know basic chemistry, you know that when we increase atom amounts or we change substances or increase the atoms being used, we also have to balance the rest of the equation. And since we have more carbon and more hydrogen being reacted in our ethane reaction, we need to account for that with our ratios of oxygen and our CO2 and our water being produced in our combustion reaction. So to make things a little bit more simple, we're going to leave a gap for our coefficient or the number of molecules being reacted. So we're going to leave a little gap here. So our oxygen component and then our nitrogen component. And that's our left side or our reactant side. And we're going to have a coefficient for our CO2. And then we're going to have a coefficient for our water. And then we're going to have another coefficient for our nitrogen. So you might be wondering, where do we start? So we're just going to start with what we know so far. We know that, and more, actually before I start this, we're in most chemical equations, ethane and sometimes methane will then, in our ethane reactions or our ethane combustion reaction, it'll usually have a coefficient. But we're not going to use a coefficient in at least not this portion of our problem here on the ethane reaction, just to keep all of our ratios consistent. As long as we're consistent with our ratios, we really don't need to worry about what ratios are going to be what our ratios are going to be between atoms, as long as they're consistent and they're balanced. So we're going to start with our pure ethane. our ethane natural gas. So what does this tell us? Our ethane is composed of 2 carbon and 6 hydrogen. So we can immediately rule out, or we can immediately say that that we have 2 atoms, or sorry, 2 molecules of CO2, because there's only 1 carbon atom being represented on the right side of the equation, and there's 2 carbon atoms being represented on our left side. So we can immediately say that two molecules of carbon dioxide are being reacted on the right side, which then makes a balanced equation with our ethane. And then, since we have 6 hydrogen reacting, we know that there's going to be 3 molecules of H2O, because when we have 6 on the other side, we have 6 on the right side. So from here, we then need to find a ratio of our oxygen that's being reacted on the left side compared to our right side. And we need our atoms on the right, or our molecules on the right side, to figure out what's going on here. So since we have 2 molecules of our CO2 being reacted, we know that this here, our carbon dioxide, is then going to produce 4 oxygen in total with our ratio or coefficient given. And we also know that that we're also going to produce 3 oxygen with our water, because that's the coefficient that's standing in front of that. So we definitely know that a total of 7 oxygen is going to be reacting on the right side. So you might be thinking, so how do we represent that on our left side of the equation for our ratio? As you can see, we have 2 atoms of oxygen being represented here. So we can then say that our ratio is 7 oxygen compared, or 7 oxygen over 2 atoms of oxygen. And in more basic terms, it's also a ratio of 7 over 2. And more just to make things clear, since we have 7 oxygen reacting the right side, we have a ratio of 7 over 2. And since we have 2 oxygen reacting on the left side, in a more just mathematical sense, just to make it a little bit more clear, since we have 2 oxygen reacting here, we can then say that our oxygen multiplied by our ratio that we're going to give it is going to result in 7 oxygen on the right side. So this proves that our ratio is correct, that what this side is going to produce is also going to produce on the right side. So we then have a balanced equation. So just to get rid of this last portion here, to make it a little bit easier to read, we then have the ratio of 7 over 2 oxygen atoms, and then 7 over 2 nitrogen atoms with its already built-in ratio with air. And then we have to do the same thing on our right side. And then we're going to move on to our propane reaction. So our propane reaction is going to be, we're going to solve it in a very similar sense. So our propane reaction is going to be consist of 3 carbons and then 8 hydrogens. And we're going to set this problem up in the same way that we did our ethane reaction. So what we're going to do is then leave gaps. Make sure we include the ratio of our nitrogen. So now we have everything set here. So starting where doing the same process we did when we started our ethane reaction, we're just going to solve it the same way we did with our ethane. So we have 3 carbons, so we can immediately say that we have 3 molecules of carbon dioxide on the right side. And since we have 8 oxygen being reacted here, We also know that there's going to be 4 molecules of H2O or water being produced over here. And with these two coefficients, we then know that 6 oxygen here plus 4 oxygen here is going to result in, mess that up a little bit. We also know that 10 oxygen is going to be produced in this reaction. And doing the same thing from before, we also know that 2 of our oxygen is being reacted on the left side, and then it's going to end up resulting in 10 oxygen. So what ratio that we're going to have is going to result in this? So it's going to be a ratio of 5. And this, so it's going to be 5 oxygen on the left side that's going to react together with our propane to result in 6 oxygen here and 4 oxygen here. So we can then plug that coefficient in to the rest of our problem. So it's going to be 5 molecules of our oxygen, then 5 molecules of our nitrogen. And then we're also going to have 5 molecules of nitrogen being reacted here. And this is our moles, or this is our stoichiometry that's going to help us produce our calculations in later parts here. Because this is going to be used to figure out what's reacting and how much heat it's going to produce. And our nitrogen is going to play a part in this, because if we didn't include our nitrogen, it's also going to change our temperature instead of having pure oxygen.